Hello all. Um, I'll be doing a lecture on the reasoning segment. So if you were more interested in Hume, you'll be doing this track, or at least you can see if you like what you see, and then decide as we go along. So as you can tell, I'm doing a video lecture. That's because I'll be in Florida presenting at a conference this weekend. So unfortunately, I'll miss lecture. The software that I have doesn't have many features, so basically you're going to listen to me talk, and then I happen to be behind a convenient whiteboard, so if I need to do any sort of drawings, I can just go back there and do that quickly. My intention is to make this 20 minutes long, and then you're done. But this will be a substitute for lecture, so hopefully you can give me that much time, and I promise you'll benefit as a result. So I am going to closely follow what Blackburn does in the reading for this week. It's probably some of the densest reading we've done so far, and I think it's worth just reiterating. I'll probably go over a lot of this material again next week, but I definitely think it's worth talking about in a little bit more detail. And one of the great advantages that you have as a result of this being a video is that you can review sections, and I'm going to try to go in order of the material that Blackburn presents. So if you want to spend extra time on truth tables, you can reread that section of Blackburn and then rewatch my video, stop it, maybe rewatch small portions or something like that if that's helpful. And I'll try to provide some supplementary materials like some key concepts, and of course we can always meet at office hours or any time that you can meet and deal with this stuff. But I think it's important to learn, and I do think it's a little bit technical. So the first thing that Blackburn deals with is somewhat review. So in terms of just arguments, right, that's what we're dealing with in reasoning. He discusses premises, right, and if you're going to reject an argument, you want to either somehow show that the premises don't entail the conclusion, which suggests that the argument is not valid, right? This is review, or that the argument is unsound, which either means that it's invalid or that some or one of the premises is false. Right. So the first novel thing that Blackburn does is truth tables. So truth tables are an interesting way to show the various possibilities just based on truth values, true and false, nothing else. You might think of it, for those of you in computer science or something, just like a binary ones and zeros sort of thing. So you can just take any old proposition, P, right? P, and assign it the value of either T or F. So true or false, those are the only two options. Is that visible? Barely visible. We'll switch to black. Right. So true or false. So this seems trivial enough. It is in a certain way. You might think there's gray areas, and those gray areas are more a matter of us knowing or not knowing something. But we tend to think that there's either the case that there's a unicorn in the room or there's not, right? There's some gray area in terms of determining what that means or those sorts of things, but basically it is or it isn't. So some of the more interesting work that we can do with truth tables is assess more complicated propositions. So we'll take the example of P and Q. So how can we assess in what conditions P and Q is true? We can assess this by looking at its constituent parts, the sort of atomic propositions that make up this molecular proposition that is the conjunction of P and Q. So the way we can do this is by assigning various different truth values to both P and Q. So if we say that P is true and Q is true, right, we can go through and say, okay, so P is true, right? We already assume this part, so we just apply it over here, and then Q is true, so we say Q is true. And when we use this symbol, the ampersand, it's and, it's a conjunction, and the only condition under which this and is true, a proposition with a conjunction is true, is if both parts of the conjunction are true. So we can ask ourselves, are both parts true? If both parts are true, then we can say true. And so now we know that's the truth value of P and Q if we know these truth values. And so this is a necessary consequence. This truth of this P and Q is a necessary consequence of P being true, comma, Q being true. This is a very trivial example in a certain way, but it emphasizes the point of just how strong of claims these are. It has to follow. Maybe a little bit more complicated example is the case in which P is true, but Q is false, right? So in this case, we would go across and apply P like this, Q is false, and remember the meaning of P and Q is if both sides of the conjunct are true, then the whole thing is true, right? So you look, both sides no, so this is going to be false, right? We can do the same thing. And then, of course, if neither are true, this is also going to be false. So this is a way to analyze all sorts of propositions. You can do it in much more sophisticated ways, but that's the most basic element. And I'm worried that this is slowing down. I see it kind of lagging, and I'm hoping that's not passing over to the actual footage. But one of the things that this shows is that this system can show you which rules of inference are good. And by what I mean by a good rule of inference is a rule of inference that won't take you from truth to falsity. If you already have truth on one end, it will result in true outputs, right? So you can certainly know from these certain inputs what sort of output you get, and that's a good rule of inference. So one example that I think is easy enough, sticking with the AND example, is conjunction elimination. Conjunction elimination is just the general rule that if you have any conjunction of propositions, right? If this is true, either part will also be true, right? So that just follows. So if you have this, you can just do, they call it AND elim, right? And then so you know that P is true, just as a result of this, right? It just necessarily follows. Because in a sense, what it means for P and Q to be true is also for for P to be true. And then also, you can do this for Q too, right? So that's just a necessary entailment. So you can see how if you already had a true proposition such as P and Q, you're never going to end up, and along with that, a good rule of deduction like AND elimination, you're not going to get a false result. If you had a rule of inference such as like AND introduction, say, AND introduction would be like, we'll call it this. I don't want to compute, or and making up additional propositions or something. Then I could be like oh, and C or something, right? And that would just be and. That's what I mean by and introduction. That's a rule where you can just, if you have any proposition, you can just go P and Q and C and D. But clearly that rule of inference isn't going to ensure the truth of the consequence, so it's not a good rule of inference. Right, so that's what we're trying to ensure. And so the next sort of thing that Blackburn addresses is contradictions and tautologies. So contradictions are things that are necessarily false. Like always false. It just always leads, that's very small, to a contradiction. Right. So a famous example of that is P and not P, right? So assuming at the exact same time that both P and not P are true. So we can see why this doesn't work if you apply the truth table method. So I'll try to demonstrate. So the only variable here is P, right? And so we can apply two different values to P. We can either say we can assume P is true or P is false. Right. So let's start with this case. P is true. So P is true, this is true, and this is true. But the whole point of negation is to say not in front of the sentence, right? So the negation of the statement, it is raining, is it is not raining, right? So that is a contradiction of it is raining. So instead of a T here, you go and put an F, right? Because this is the operand, right? Kind of like math. And so then you'll see that there's a true and a false side by side. And since we already know the result of our conjunction from earlier is that for this conjunct to be true, both parts must be true. And so we can see that this is true and this is false. So this is going to be false. Right. Uh-oh. Falling asleep. Right. So now we'll do this with falsity, and some of you may have already predicted this result, but it's an interesting result nonetheless. So we'll say this is false, and this is false, right? But since we're applying the same negation, the opposite, it's like a double negation, right? Not P just equals P, right? Like, same thing sort of applies in mathematics. So it isn't not raining. Well, that's a bad example. Anyway, this is clear enough just in this case. We know that this negates that. So there's only two states of affairs that it could obtain, either true or false. So if it's not false, if it's the opposite of false, it must be true. So we see once again that these are going to be inconsistent with each other. They have opposite truth values. And this opposite truth value will mean that the conjunct is going to fail. Right, so it's a contradiction every single time. And so that might be pretty commonsensical, but it's just a formalized way of showing something that we've already kept in mind all along. And I think an important thing that Blackburn is right to point out, and that's significant, is that when we get into more complicated cases, these things stop being so intuitive. It becomes difficult to keep track of how many propositions are operating and all the various logical connectives. So this formalized method ensures that we don't lose track of these things and get into fuzzy area where we think something that's true is false or vice versa, or that valid things don't obtain or whatever. I'm short on good examples right now. So the opposite of a contradiction So a tautology is always true. A tautology is also something that's a priori true. It's a necessary consequence of logic that it is that way. You don't need to go investigate the world to find out things like A equals A, right? That just is the necessary truth of the way things are. So there's a lot of tautologies that aren't obviously tautologies, but will prove to be such once you analyze them a little bit more closely. So here we are. We can add a not to this. So applying the same truth table method that we already used, we'll initially, and you'll kind of see how this works outwards. So we'll apply a true here and a true here, right? And then you see, oh look, it's false. And so we're looking at this one and this one. These are inconsistent, so this doesn't obtain, so this is false, right? And so now we're looking at this one and this. This is the negation of this false claim. So the negation of a false claim is true, right? It's the opposite value. So true is what we're going to get, right? And then if we plug in false, false, true, right? And then we look at these two and we see, oh look, they're inconsistent. They're not both true at the same time. Then we'll get this false result. And then what's the opposite of that? The negation of the false is once again true. So under either possible scenario for P, it always is the case that this assertion, it is not the case that P and not P is true, right? That's a tautology. So if you want to make it in a commonsensical sentence, I know I've used this example of raining before. It is not the case that it is both raining and not raining. That seems trivially true, right? That's just necessary analytic meaning of the terms that we're dealing with. Right. So these are interesting results of truth tables, and a further development that occurred only recently is that of quantification, and I'm going to save that for a distinct talk because that's a bit to deal with right now. That's the nothing to be afraid of section, in which Blackburn discusses the developments of Frege and Russell in terms of quantifying variables so that we can deal with, like, there is such a person such that, or every individual is such as, so we can distinguish between the quantity of the claims, right? There's a lot of good examples of that. It's sometimes called predicate logic or the predicate calculus. So yeah, but we'll deal with that in a bit. So see you guys next time.